Good afternoon, viewers. I am Dr. A.K. Wazalwar from DESM, that is Department of Education in Science and Mathematics, NCERT, New Delhi, and I have with me my colleague Dr. T.P. Sharma, again from the same department, that is Department of Education in Science and Mathematics, NCERT, New Delhi. Today we have come here to interact with you something about the sets that you normally study in class 11. The sets, as you know, in the common parlance, we use certain words that are synonymous to this word, but not exactly they convey the same meaning. For example, I may say a flock of birds, a group of people, a crowd of people, you can say, or some such words that will mean that there are certain collection of objects at a particular situation, in a particular context. Now all these words together, they mean that it's a collection, which means there are certain objects that are involved in that particular group that we say. Now this particular idea of collection has been taken and quantified. We quantify this collection as, we call it as set. So what is a set? This set you study in class 11. We say that a set is a well-defined collection of objects. These objects in a certain situation could be birds. These objects could be something that in a room, whatever objects are placed like chairs, tables, fans, etc. Or in the case of numbers, when we say we have a group of numbers under certain defined conditions. Now when I say well-defined collection of objects, I mean that, for example, when I say all the rivers of India, so when I say all the rivers of India, it will mean, and when I say Ganga is a river in India, so in this particular collection Ganga will be one of the objects. But if I say Nile, it will not be an object of this collection, because I am talking about the rivers of India. So either I can say that that particular object is from that collection, or that object may not be from that collection. If I am able to definitely say that, I will say that it is well defined. Then what is not well defined? If I take, for example, if I say the collection of best batsmen in the world, now the word best is relative. For me, X person will be, X batsman will be the best, for someone else Y will be the best, and so this is a relative word, and so we cannot say that this particular collection of say persons or batsmen will not form a set, because it is not well defined. You at particular instant you cannot say that X is best or Y is best or Z is best, and so on. So we are not able to define it. So we say that a set is a well-defined collection of objects. It could be a collection of students in a class, it could be a collection of teachers in a school, it could be a collection of staff members in an office, so on and so forth. It could be objects in this particular room where I am sitting here, the chairs, table, fan, lights, etc. All these could be the objects of this particular set. So that is what we initially mean by sets. Would you like to give some example, Dr. Sharma?
Yes, I would like to give some of the example. Dr. Wazalwar has rightly mentioned about the sets. These are some of the example of sets, like odd natural numbers less than 10, like the rivers of India, the vowels in English alphabet, various kinds of triangles, prime factors of 210, namely 2, 3, 5, 7. This is solution of the equations x square minus 5x plus 6 is equal to 0, where solutions are 2, 3. These are some of the example of sets.
So when you write these names, for example, the natural numbers less than 10, you will say that it is 1, 2, 3, 4, 5, 6, 7, 8 and 9. You will be writing them at one place. It's a collection of these numbers under the defined condition. Then similarly the rivers of India, this example I have already given. The vowels in English alphabet, that is A, E, I, O, U, it's again a collection of things which I have given. There won't be any doubt that whether A is a vowel or not, it is already a specified thing. So whether A is a vowel or not, there is no doubt about it. If I say B, B cannot be an element of this set because B is not a vowel here. So it's a well defined collection of objects. Similarly, the other examples have also been given by Dr. Sharma. Now, after defining a set and after knowing what a set is, the collection of objects, as I said, well defined collection of objects, not just the collection of objects, a well defined collection of objects, as we call it as a set. Now we need to represent, when we collect these objects at one place, we represent it in bracket, we put it in a bracket and we quote it with a symbol, and these symbols normally are written as capital letters, say capital A, capital B, capital C, as is indicated here. So these letters A, B, capital letters A, B, C, D, E and so on, or capital P, Q, R or capital X, Y, Z, normally by these symbols we denote a set. So we say A is equal to the set of all birds, or A is equal to the set of all numbers between 10 and 20, so on and so forth. And yes, you can further tell about these small letters.
The small letters generally will use to denote the elements of a set, because every set has an element, so the letters elements are denoted by small letter A, B, C, D, D, F, etc. Now
for example,
there is a set A which is a set of English alphabet, which is A, E, I, O, U. So there is a two method by which we can represent the set. One is we will write all the elements of a set like A, E, I, O, U. In the second case, we will write only one element, then we will write the property.
For example, I will just try to interfere here a little bit. When I say element, for example, I say that the set of all natural numbers from 1 to 10. So 1 is an element of that set, 2 is an element of that set. So we formally call that particular object of that set as an element of that particular set. And there are two ways of representing a set, because it is not just the listing. The listing has to be done in a certain way, and that particular way, there are two ways of representing that. One is called the roster method and the other is called the set builder form. So in the roster method, what we do is we merely put a bracket here, a curly bracket, and we list out the elements of that set. For example, 1, 2, 3 and so on, or as he has just now shown, A, E, I, O, U. So this is the roster method in which we represent a set, whereas this is a set builder form. What happens in a set builder form? As in the case of roster method, we simply list out the elements, whereas in the case of set builder form, we first write a symbol and then we describe that particular symbol as to how it is defined. For example, let me quote the same example first. For example, the set A, as I said, this is the roster form. In the set builder form, you can see that we have represented this as with a symbol X, and we have described this particular symbol. This X represents a vowel in English alphabet. So when we say vowel, it obviously means it is either A or E or O or I or U. So we ultimately end up with the same set. But this is a way in which, in a short way, through description method, we try to describe that particular element and form a set. And we read it as the set of all X. Can we show here? The set of all X such that these two dots will represent such that X is a vowel in English alphabet. If I take another set, say B, in the roster form, I will write it as suppose 2, 4, 6, 8 and so on. Then in the set builder form, the same set can be written as the set of all X such that X is an even natural number. You can see all of them are natural number and they are even numbers. So I can describe this symbol by saying that X is an even natural number. So when I go back to the roster form, I will write it in this particular way. Yes.
There are some more examples of roster form and set builder form. First is the set C, which is containing the element 1, 2, 3, 4, 9, 12, 30, 36, and in the set builder form, same thing can be written as X such that X is a natural number which divides 36. Because from here also, if we simplify, we will get the same set. Like we have a set D which is 1, 2, 3, 4, 5, 6. This is in the roster form, and same we can write as set builder
So
form.
if the set builder form is given to you like set of all x such that x is a positive integer and x square is less than 40, you list out all those positive integers whose square is less than 40 and you end up with this, that is 1 square is less than 40, 2 square is less than 40, 3 square is less than 40 and so on. So you get this particular list which we call as the roster form. The next set, one thing that is to be noted about the sets is all sets cannot be described in the roster form. All sets cannot be described in the roster form. For example, the set of real numbers. That particular set is so dense, there are so many elements in that particular set. Between any two real numbers there would be infinite number of real numbers. So it is not possible to list out the real numbers because there won't be any ordering there, and so that particular ordering thing cannot be represented properly in the roster form. So we can say that the set of real numbers cannot be described in the roster form. You can of course write it in the, if there is any condition there, you can write it in the set builder form. Yes.
And there is one more. Please note that while writing a set in a roster form, an element is not generally repeated. That is, all the elements are taken as distinct. For example, we have taken the word alloy. Alloy has, we have 2L, but here we have to write XX A L O Y. So elements may be, one element may be more, may be repeated 2 or 3 times, but in the writing of the set we will write only one element.
So in a set, whenever we write certain elements, even if I write say 1, 2, 3 simply, it means that this 1 can be taken any number of times, 2 can be taken any number of times. What we mean is 1, 2 and 3, these are the 3 distinct elements of that particular set. So when we talk about set, this distinctness of the elements is important. Even if I say the set is 1, 1, 2, 3, 1, 1, 2, 3, it will be written as 1, 2, 3. It will represent the same set. So that is how we represent a set. Now we have certain examples of sets. For example, we have this set in the set builder form, the set A such that set A is a set of all x such that x lies between 1 and 2, that is 1 is less than x is less than 2 and x is a natural number. This we are talking. Now do you have any natural number between two numbers like 1 and 2? You will say that there are no natural numbers between 1 and 2. So which elements will be there in this particular set? There won't be any element in this particular set, and so we say that this particular set is an empty set because it contains no elements. So an empty set is a set in which there are no elements. It is called a null set also, or it is called an empty set also. The other example is, yes.
Another set is, we have taken B, which is x such that x square minus 2 is equal to 0, x is a rational number, because if we simplify this equation we will get x is equal to plus minus under root 2, which is not rational. Therefore this set also empty. Third example is x such that x is an even prime number greater than 2, because prime number, smallest prime even number is only 2. So in this case also we will get empty set. In this case also, case 4 D, we have taken a set where x such that x square equal to 4 and x is odd, because if we simplify this equation we will get x is equal to plus minus 2. So this is also an example of empty set.
So empty set is a set in which we have no elements, and this is denoted normally by either empty curly brackets or the symbol phi. So we call it a null set or an empty set. Now we have this example, yes.
This is, now we are going to talk about the finite and infinite set. Because finite set, let us take a set A, E, I, O, U. Here we have a limited number of element, because this is and here we can take B. B we have 2, 4, 6, 8, and this is, we can extend whatever up to whatever time we want, we can extend. So this is the case of finite set and this is a case of infinite
So you can
set.
see the difference that in this particular set the number of elements it terminates at some place, whereas in this particular set the element this particular sequence does not terminate, it goes on, and so we say that this is an infinite set. It contains infinite number of elements, whereas this particular set contains finite number of elements. Now in the context of finiteness and infiniteness, I would like to say that when I say the singleton set 1, it means that it is also 1 1 1 1 1 any number of times, but that doesn't mean that it's an infinite set. So the distinctness of the elements, I will repeat again, plays an important role here. Here you will see that the numbers are distinct. 2 is different from 4, is different from 6, and so on. So we have got infinite number of distinct elements in this set, whereas the set which I quoted, the singleton set 1, in which you can take 1 infinite number of times, is not an infinite set, it's just a finite set, which we call as singleton set, containing only 1 element. Yes.
These are some of the examples of finite set. Like first one, the set of days of the week, because days of the weeks are always fixed, there are 7, therefore this is a finite. The set of the solution of the equation x squared minus 6 is equal to 0, because if we solve this equation we will get plus minus 4, so the solutions we have only 2, that is a finite. 5, the empty set, x such that x is n and such that x minus 1, x minus 2 is equal to 0. If we solve this equation, we will get x is equal to 1, x is equal to 2. So this is also a finite. Similarly, in the 5th case, here we are getting x such that x belongs to n and 2x minus 1 is equal to 0. If I solve this, we will get x is equal to half. This is also a finite. So these are the cases of finite sets. Now these are some of the cases of infinite set, because through finite case we understood that there are limited number of elements. In case of infinite set, there will be a enough number, because whatever we think, and after that we will get one more number. If there is n is a last case, then there will be n plus 1, n plus 2, n plus 3. The example is set of all points on a line, because there are infinite number of points. And second, x such that x belongs to n, x is a prime, because there are prime number, there are many prime number, and x belongs to n and x is a odd. This is, in this case also we will get infinite element. The set of positive integer, because in this case also we will get infinite element. The set of even natural number, in this case also we will get enough set or many elements. That's why these are some of the example of infinite sets.
So when I say the set of numbers between the numbers say 1 and 10, natural numbers, when I am first putting the condition natural numbers, so there would be finite number of natural numbers between 1 and 10. But if I say the number of real numbers, between 1 and 10, then that will become an infinite set, because there are infinite number of real numbers between 1 and 2. You can just go on dividing that. Suppose between 1 and 2 if I want, I can say 1 plus 2 by 2, that is 1 by 2 is there. Then between 1 and 1 by 2, I have got 3 by 2, 1 plus 1 by 2 divided by 2. So in this way you can get on and on with the numbers between any two numbers, and this particular thing becomes infinite. So that is another example of an infinite set. Yes. Now the next point, we talked about sets, we talked about how we represent the sets symbolically, we talked about how we represent the sets in different ways, that is the roster method and the set builder method. We need to be fluent enough to use this particular vocabulary to understand the concepts of sets, so that we can think more about it, because the concept of sets is the basic concept on which the entire mathematics is dependent. And the concept of calculus, whether it is differential calculus or integral calculus, everything depends on the concept of sets. So we need to be very clear about it. Now when we talk about the sets, we also talk, if we take them as elements. So for example, when we define the operation of equality, suppose, so we have got certain notion about it. So what do we mean by equal sets? So when I take a set A and set B, for example, if I take the set A as 1, 2, 3 and the set B as 2, 3, 1, the order in that particular set does not matter, but you will see that the element 1 is in A as well as in B, the element 2 is also in A as well as in B, the element 3 is in A as well as in B. So we find that every element of set A is also an element of set B. So in this case we have got the notion of equality between the sets. We say that set A is equal to set B or A equal to B. So we have got some more examples for equality of sets.
So like A 1, 2, 3, 4, B 3, 1, 4, 2, these two are equal. Sir has already, Dr. Wazalwar has already explained. And number 2, A is a set such that X is a prime and S less than 6, and P is a set X such that prime factors of 30. So in this case, in A case also we will get 2, 3, 5, and P also will get the element 2, 3, 5, therefore A is equal to P. So we can find out more example of equality of cells.
Yes.
Now we will talk about the subset. Suppose there is a set A, X, Y, Z, and there is another set X, Z. So in this case, this set B is smaller than A, and all the elements of B are in A. So we say that B is a subset of A if all the elements of A, B are in A. So
after the concept of equality of two sets, we have this particular thing that a set may contain less number of elements, the other set may contain more number of elements, but the elements that are in B are also in the set A. In that particular case, we say that, I mean, it is equality and inequality sort of thing. So in this case, we say that B is a subset of A, because every element of B is also an element of A. X is in B, X is in A, Z is in B, Z is in A. We say that A is a subset of B. But in the formal mathematical way, we express it as, yes.
Here we can define A is a subset of B if A belongs to A implies A belongs to B. That is, A is a subset of B, every element of A is also an element of B. That is, if A is a subset of B and B is a subset of B, then we can write in this case A equal to B, or these two sets are equal.
Because when we say that A is a subset of B, it means that every element of A is also an element of B, and here every element of B is also an element of A. So naturally it leads to A is equal to B, because both of them have got the same number of rather the same elements in both the set. So informally we in mathematics write it as A is a subset of B and B is a subset of A if and only if A is equal to B. Yes.
Now there are some example we can talk about, example of subset, like every set is a subset of itself. Second example, set of Q. Rational number is a subset of real number, natural number is subset of real number, integer also subset of real number. So we can write n is a subset of integers, and integer is a subset of rational number, and rational number is subset of real number.
Let me add in this particular thing, when we formally write the sets, the sets that we have studied till now, though we didn't study them as sets, we studied them as collection of numbers, we can say. So the first one was the collection of natural number, that is 1, 2, 3, 4 and so on. This particular thing in the case of sets is denoted by the capital letter N. So N is nothing but the set of natural numbers, and then comes the set of whole numbers when we put 0 in it. So it starts from 0, 1, 2, 3, 4 and so on, we call it set of whole numbers, and when we add negatives of these numbers to it, we get the set of integers, that is Z, it is represented by Z, that is set of integers. And then we have the set of rational numbers, which is denoted by the symbol Q. These are the standard symbols that are used throughout in mathematics, and this R represents the set of real numbers. So Q is nothing but a rational number. It's a number of the form P by Q, where P and Q are integers and Q is not equal to 0. So such numbers like -1 by 2, 2 by -3, In fact, 1 is also a rational number, because I can write this 1 as 1 upon 1 or 2 upon 2 and so on. In fact, I can write minus 3 also as a rational number, because minus 3 is minus 6 by 2 or minus 3 upon 1, whichever way you choose. So every integer you can write as a rational number. So a rational number is a set of numbers of the form p by q, where p and q are integers and q is not equal to 0. Then the numbers that are not rational numbers, we call them as irrational numbers. For example, square root 2 or pi and so on. So the set of rational numbers and set of irrational numbers together, when we keep them together, we get the set of real numbers. So real numbers is the greatest of all these sets, and you can see from this particular thing that all these sets are subsets of the set of real numbers here. Please continue.
We have a one, because I have taken from this mathematics kit, this is we can say C is a subset of B. So here C is contained in B, therefore C is a subset of B.
Here in my NCERT we have developed a mathematics kit for class 12, class 11 and 12, in which we have developed these kinds of models to represent, to visualize the sets. And here, as Dr. Sharma explained, this is the innermost set. This is we call it a subset of B, and this B is contained in this set A, so we say that B is a subset of A. So eventually this C becomes a subset of A also.
Now we can talk about the interval as a subset of R. Like AB is an open interval where A and B are the real number. So these are, and this is a closed interval, and these are again a subset of R. This is a real number.
For example, on the number line, when you plot the numbers on the number line, you have got 0, 1, 2, 3 to the right of 0, minus 1, minus 2, minus 3 to the left of 0. If I take the interval from 0 to 1, if I take all the real numbers, as I said, there are infinite real numbers. You can tell me what kind of set it will be. So if I take the set from, the interval from 0 to 1, excluding 0 and 1, that means 0 and 1 will not be included in this set, but rest of all the real numbers will be, between these two numbers, will be included in that particular set. So it will be an infinite set. And this is called an open interval 0, 1, as he described there, open interval AB, that is a set of all numbers, real numbers, between A and B. If I take the number 0 from one side in this set, then it's a closed set from one end, that is closed interval 0, 1 and open interval 1, that is what we call it, because 1 is not included in the set, whereas 0 is included in this set. Similarly, we have, if it is included, both the endpoints are included in the set, we call it a closed interval. So it's a closed interval 0, 1. Here we have taken some general numbers like closed interval AB. So closed interval AB is a set of all real numbers such that A is less, such that these numbers are lying between A and B are also included in this particular set. So these are the four types of intervals we get. One of the endpoints may not be included and the other endpoint is included. For example, here one of the endpoints is not included, the other one is included, for example here, and both the endpoints are included, which is called the closed interval. Both the endpoints are not included and we call it an open interval. So these four kinds of intervals we get, and they will form a set, because it's a well defined collection of real numbers between these two numbers. So in general we call all of these as intervals. So every interval is also a set, and it is a subset of R, that is set of real numbers.
Now we will talk about the power set.
So just as we constructed sets of different numbers of different objects, if we take the sets in themselves as objects, then we get a set of sets. That is, if I take a set, say A equal to 1, 2, 3, please.
So suppose A is a set containing element 1, 2, 3, and from here we can form a subset like phi 1, 2, 3, set having element 1, 2, set having element 1, 3 and 2, 3, 1, 2, 3. So total we have, so power set of AR phi.
So collection of all these elements here will be the power set of this particular set. So dear viewers, we have till now discussed about sets, the representation of sets, the different ways in which sets can be formed, the different operations we have not discussed yet, but we have discussed something about subsets of sets, and the collection of all these subsets of a particular set, that we call the power set of A. So that was all our deliberation till now. We can extend this particular concept further when we talk about operations on these sets. Just as we have got operation on numbers, we have got operations on these sets also. It is union, intersection, difference, and so on. But how these operations are done or how they are defined, we will be taking it up in some of our next session whenever we interact together. So till then, we say goodbye. Thank you.